Let's wait for a couple of minutes, then I will start. Okay, let me start. So this is the week 8 of the course, Introduction to Atmospheric and Space Sciences. This is the 8th problem solving session. Here also we will discuss the assignment of the 8th week, and we will discuss about the ionosphere mostly, because the next assignment will be particularly on this ionosphere aspect, and we will discuss different layers of the ionosphere. And just a minute. Different layers of the ionosphere and how they are defined, and during the daytime and the nighttime, what is the diurnal variation. Then in the solar minima and the solar maxima, what are the variations, and some small characteristics I will give in the D layer, E layer and F layers, and some small numerical which will be helpful for assignment solving. and some more aspects about ionosphere, different reactions which we can see in the ionosphere. And again, based on these reactions recombination rate, there is an example numerical, and this numerical is also will be helpful to solve the assignment. And then particularly for the Chapman's theory and its assumptions and the derivation which is also there in the NPTEL study notes. You can follow that, as well as this derivation is helpful here also we will derive. Okay. So at the very beginning I will start with the assignment questions. Okay. The first question is, raindrops are about how many times larger than the typical CCNs in size? Now, the size of a typical CCN, just a minute. Okay, the size of the typical CCN, what is CCN? CCN is the cloud condensation nuclei. Let me write it. Cloud condensation nuclei. Its size is about 0.2 to 2 micrometer. Now, if CCN size is 0.2 to 2 micrometer, and we also know that size of a raindrop, a typical raindrop, is about 1000 or 2000 micrometer. Now, this 0.2 times how much is actually 2000. I'm taking 2000, you can take 1000 also. So nearly it will be about 10,000 times, right? Because 10,000 into 0.2 if you do, then it comes out to be 2000 micrometer. Therefore, the size of the raindrop is about 10,000 times the size of the CCN. Therefore, the correct option here will be 10,000. Okay. Second question is based on the Doppler effect, and it is easy to understand also. In which of the following situations the Doppler effect will present? First option is the source and the observer are moving towards each other. Second option is the observer is moving towards the source, or the source is moving away from the observer. See, in all the cases it is applicable. There is a source and there is an observer, and our frequency is C upon C minus V. So in this way, I have also already discussed this Doppler's shift in frequency and how to calculate the frequency of the observer, frequency of the source. And in Doppler's effect, both things are considered, that if the source is moving away or the source is moving towards the observer. Similarly, if the observer is moving away or the observer is moving towards the observer, or both are moving in the same direction. All the three things are applied in the Doppler shift or Doppler's effect. Therefore, all of the situations considers all situations. Okay. Therefore, all of these should be the correct option. Third question is, when a substance is dissolved in a pure water, then the saturation vapor pressure will. The question has a very important word here. When a substance is dissolved in pure water. Now, what is the meaning of pure water? No salts. Now, if salts are present, suppose this is a container where some salts are also present, then what it will do? It will close the gap and it will not allow the molecules to evaporate or vaporize. Also, some salts like NaCl makes bond with water. So this Na plus is there, and you have two oxygen like this way. It forms bond. So it does not allow the water vapor molecule to uh, just vaporize away. Therefore, if there is a pure water, then what will happen to the saturation vapor pressure? It will decrease. Why? Because is not allowing to evaporate. If it is not allowing to evaporate, not enough vapor molecules will be present, and hence the saturation vapor pressure will decrease. Simple thing is that suppose you have this and no salts are present. Yeah, when a substance is dissolved in a pure water, now I include some salts. Now salts are given because substance is dissolved. So as the salts are given, it form bonds like this, and as a result of which what happen is that vapor molecules cannot vaporize over this particular area. So here less number of vapor molecules. Hence saturation vapor pressure decreases. Or another way you can say, salts results into decrease in evaporation and that results into decrease in saturation vapor pressure. That is the key concept. Okay. Now the fourth question, which of the following's droplet size the curvature effect will be minimum? So the option here is small, medium, large, and same for all sizes. The correct option is large. Why? Minimum. It has said that curvature effect is minimum. Remember this curve. Okay, this is the first I have done, second, and this is corresponding to the third. So for the fourth, this is the thing. See, curvature effect is what? See, this is the supersaturation. Remember the curve, Kelvin's equation. And this is R. So radius is decreasing here, radius is increasing here. So more the radius is increasing, this effect becomes this. So more this is the Kelvin's equation. Kelvin's equation. So what happens? You can see that as the R increases, R becomes large, the Kelvin effect is less or the curvature effect is less. Therefore, as R is large, is less. Fine. Just wait a minute. Fine. Now, the next question is, the force required to remove a molecule from a curved surface is dash the force to remove the same molecule from the plane surface. So the answer is that the force required to remove a molecule from a curved surface is less. Why? I have discussed in the earlier class, the earlier problem solving session. So you have a droplet or curvature is more here, and curvature is less in a plane surface of pure water. Now what is happening here is that more molecules are there nearby, which is creating bonds with this water molecule and does not allow this water molecule to leave or evaporate. And this tension is known as the surface tension force. But in case of this curved surface, the surface tension is less. Less molecules are there to pull. So if this is the water molecule which it has to evaporate, small water molecules are present here, which is creating a binding force, but it still can easily vaporize. Therefore, more number of vapor molecules are there, and since the surface tension is less, you can give less force. Force 1, and here it is force 2. So force 1 will be always less than force 2. Simple. Because the surface tension force, which is actually not allowing this water molecule to move, that is less here. So less force is required to pull up this molecule and make it vaporize, which is not in the case here. Okay. The SI unit of surface tension is, the SI unit of surface tension is Newton per meter. It is actually surface tension which is denoted by sigma is actually force per unit length. Fine. So this is the we call as the force due to surface tension. This is the force due to surface tension. Right? And this is the L, the unit length. Fine. Therefore, it will be Newton. The force SI unit is Newton and length is meter. So Newton per meter. Okay. Seventh question is, which of the following is or are true for curvature effect? See, curvature effect helps in formation of raindrop. Due to curvature effect, the rate of evaporation increases. Of course, this is the right answer. Due to curvature effect, the rate of evaporation decreases, and none of the above. Of course, the rate of evaporation should increase. Why? Because as I have already discussed here, for this case, for curvature effect or more curved the surface, what will happen? Surface tension is less. Vapor molecules can evaporate rapidly, and that's why the saturation vapor pressure also goes up. Can evaporate rapidly, and hence the rate of evaporation increases. Rate of evaporation increases. Right? Okay. Fine. The next question is, the approximate size in micrometer of cloud condensation nuclei is 0.222 micrometer. I have already told in the initial classes. Which one of the following is or are correct for solute effect? Due to solute effect, condensation increases. See, solute effect has nothing to do with condensation, because what is the meaning of solute effect? You have a pure water, you are dissolving some salts. If you are dissolving some salts, it will form a bond with the water molecules. As it forms bond with water molecules, what will happen is as you form bonds with water molecules, this is the condition. You have salts given, and salts forms bond with water molecules, so it will not allow these water molecules to move, and that's why it is not allowing the water molecules to move. Evaporation is less, therefore it has a direct effect. So solute effect affects evaporation by decreasing its rate. Fine. Just a minute. Just wait. Fine. Okay. That's right. Yes. Some connection issues are there. That's right. Okay. Come back to the ninth question we have discussed, that solute effect reduces the rate of vaporization but has no effect on condensation. Fine. 10th question is, which of the following influence the growth of droplets that occurs by diffusion? So as we know that both the curvature effect and the solute effect has an influence in the growth of the droplets. It has always an influence in the growth of the droplets. Fine. Okay, so these are the questions which are present in the week 8. So now I will directly jump to the ionosphere. So what is ionosphere? Ionosphere, so let me first define what is ionosphere, and then I will talk about different layers of the ionosphere, as you can see here. So what is ionosphere? Let me write here. It is the region, let me write properly the definition of the ionosphere. So it is the region of course, the Earth's atmosphere. It is a region of the Earth's atmosphere where electrons and ions are present in large numbers and what is the utility of this ionosphere? It is that large numbers to be able to influence radio waves propagation. I will come to this later, this radio waves propagation, in this problem solving session only. So what it does, so ionosphere essentially is nothing but a layer in the atmosphere where you can find large number of electrons and ions. And how these are produced? Of course by solar radiation, because there are several molecules which are present, as we know, in the atmosphere, like nitrogen, oxygen, particularly these nitrogen and oxygens are present. Now if shortwave radiation of the solar radiation comes, which is highly energetic, how do we know that shortwave radiation is highly energetic? But remember this expression, E is equal hc by lambda. So E is inversely proportional to the lambda. So what happens? If shorter the wavelengths, larger will be the energy, and this energy will break down the molecules or atoms to ions. So this energy interacts with atoms to form ions and electrons. That is the core concept of the ionosphere. But now if you see this particular diagram, this is the Earth's surface, and this is the Earth's surface, and from here, from about say 60 kilometers to about 400 kilometers or so, this is the range of the ionosphere. Now, if you remember the earlier classes, very beginning, we have drawn the temperature profile of the atmosphere and divided certain regions, okay, like this. So this is your temperature decrement with height, which is in the troposphere. This is the tropopause, then stratosphere, then this is stratopause, and this is the mesosphere, which is having the lowest temperature. This is the mesopause, and after that there is an increase. Now, so what is this? This is troposphere, right? This is stratosphere, this is mesosphere, and this is thermosphere. Then where is the ionosphere? If this is 60 to 400 kilometer, and if you remember particularly the heights of each of these layers, so this troposphere extends say up to 15 kilometers, stratosphere up to 50 kilometers, mesosphere up to 90 kilometers, and after that it is thermosphere. Now if I am saying that it is the ionosphere is belonging from region 60 kilometer to 400 kilometer, then it should start somewhere between the mesosphere to thermosphere. It extends up to the space, right? So ionosphere, it extends, or I would say starts from mesosphere and goes to thermosphere or exosphere. Exosphere is the outermost, or exosphere. Fine. What we have learnt earlier, I have combined it with the ionosphere regions. So ionosphere, from this particular diagram, as you can very clearly see, from 60 kilometer to 400 kilometers or more is the depth of the ionosphere. And what you can notice here is that the lowermost layer is the D region. After that E, then F1 and F2. Okay, so as you go from lower to the top of the atmosphere, you get D, E, then F1 and F2. Now question is, how do we categorize these layers? I will come to this concept just now. Fine. So this is the different layers of the ionosphere, and I will discuss the characteristics of different layers of the ionosphere. Here I have defined the ionosphere. It is the region of the Earth's atmosphere where electrons and ions are present in large number to be able to influence the radio wave propagation. Of course, this also I will come. There is a numerical based on this also. And how these ions are created, the second question comes, how these ions are created. So ions are created by the solar radiation. And which kind of solar radiation? Of course, the short wave radiation. Why? Because short wave radiation have higher energy. So this higher energy will interact with these atoms or molecules to form ions and electrons. And we will see what kind of reactions we get in the ionosphere. Ionosphere depth is from 60 kilometer to 400 kilometer, which we have seen here. And already we have seen in the first or second class that temperature profile of the atmosphere, vertical profile of the atmosphere. And we have categorized several layers like troposphere, stratosphere, mesosphere and thermosphere based on temperature and moisture. And if it is extending from 60 kilometer to 400 kilometer, therefore we can definitely say that it is ionosphere is somewhere starting from mesosphere up to the exosphere. Fine. This is the concept, and we have also seen that the layers of the ionosphere are D, E and F, and where F is having F1 and F2. Fine. Now, in depth of the ionosphere layers. So you can see here the layers of the ionosphere. First is the D region. What is D region? Having 60 to 100 kilometers. So as you can see here, this is the this smallest part. This one is actually the D region. Now how this D region is created, I will come to this. Next is E region. Actually, this ion concentration, particularly based on the ion concentration, uh, let me write, based on the peak production, I would say, based on the peak production rate of ions, we can draw a profile, and wherever there is inflection points, means turnover, inflection points or turnover, you can find that is defined as a layer. I will show with a diagram. If you see this, just a minute. This one, I will draw it here. Just a minute. Now, if you have this particular diagram, it is a general, this is height, this is the number of electrons. Let us not consider the ions first, the electrons which are present, and we can see that if you see the vertical profile, it comes out like this, and it looks like this. Okay, so now where is the inflection point? See, this is the turnover, again this is the turnover, this is the turnover, and this is the turnover. Therefore, these are F2, this is F1, like this way. This is E and this is D. In this way, wherever there is an inflection point, that layer becomes the different layers, like D, E, F1 and F2. Fine. And as you can see, nearly about 250 kilometers. This is about 250 kilometers. I will come to this. No need to worry about this right now. I will come to this. That at 250 kilometers, the peak production is maximum. That is the peak production, which we call as the peak production. That is very large. Now, there is another layer it is the lower layer. Fine, 60 to 100 kilometer. Next is E region, just above this one, which is 100 to 150 kilometer. You can refer to this particular diagram as well. This one, 100 to 150 kilometers, is the E region. And after that, the F1 region occurs, which is 150 to 250 kilometers. And between F1 and F2, there is a 250 kilometer height. At this height, the production peaks is maximum. Peaks. Okay. Now, question is, here the question arises, why production is high at 250 kilometers, and above and below that, it's low. Means this concentration of electrons is low. Why? But this we will answer in the later half. So this is the F1 region from 150 to 250 kilometers. For your better viewing, this is the region, and after that F2, which is greater than 250 kilometers. Fine. Okay. Now this, how these ions are created, I have summarized here. The radiation from the sun at shorter wavelengths causes photoionization. Photoionization means some atoms or molecules, you interact with the photons h nu, and you will get ionized, like ions plus electrons, some energy maybe. Sometimes some energy is also released. So this is the production of the ionosphere, where the ions and the electrons are created using the photoionization. And what particular photoionizations generally take place? Generally the photoionization process. So this photoionization consists of what wavelengths? Of course, the short wave. I have written here the shorter waves. So what are those short waves? Generally the extreme UV radiation, very smaller UV radiation, or X-rays. These are particularly helpful photons to interact with these atoms and molecules and forms ions and electrons. This is the core theory of the ionosphere, that how the ions and the electrons are created, okay, and how these layers are determined by the inflection points. We can see wherever there is a turnover of the curve, that is the particular layer, the depth is a particular layer. And as we have already discussed, that it is extending from 60 kilometer to 400 kilometers or so. So 60 kilometer to 400 kilometer means it is starting from mesosphere to exosphere. That's all. This is the core and basic concept of layers of ionosphere. Well, more characteristics about the layers of ionosphere I am going to discuss now. See, now what is there? Here I have shown the different regions. Of course, there is another region which is there, which is the top side region, which is nothing but the magnetosphere also. It combines with the magnetosphere, and there those ions which are present, they generally move. These ions are nothing but charged particles. So these charged particles moves in geomagnetic field. What is geomagnetic field? Geo means earth. So earth's magnetic field, and starts helical motion, and finally reaches poles. Now in poles, atmosphere, the nitrogen or oxygen atoms are present. So they interact, these charged particles interact with this N2 or O2, and because of which what happens is that the electron generally goes into the excited state by absorbing the photons. By interaction it goes up to the excited state. Now as it falls, it releases a photon, and therefore we get aurora. In the northern hemisphere we get aurora borealis, in the southern hemisphere we get the aurora australis. So this is the concept of the aurora, but below which these things exists, D, E, F1 and F2, which we have discussed already. The heights I have already shown in the previous figures, as well as I have already written there. Now the peak means what? Peak production height. This is the peak production height. So this sometimes may be helpful for to answer if some kind of such kind of questions comes, that what is the peak production in D layer or peak production height of the D layer. So for that you have to remember that this is the 90 kilometer, just the end, then 110, then 200, then 300 kilometers. So these are the peak production height, and the corresponding density also you should remember, that is for D it is less, per meter cube it is less. It's about 10 to the power 8 to 10 to the power 10 per meter cube, 10 to the power 11 electrons per meter cube, 10 to the power 11 to 10 to the power 12, and it is somewhat greater than 10 to the power 12, but we say it is about 10 to the power 12 per meter cube. So this is density of electrons, right? Therefore for all the layers we have now found out that what is the peak production rate height and the electron density which is present, that is per unit volume of a section or volume, how many electrons or ions may be present in the different layers. So in the lower layers they have lower electrons, upper layers they have more electrons. Fine. Now why is it so? Why that the lower layers, now the question here again, that why at lower layers, density is low? This is because density is low is because lower layers, the photons of sun rays is already getting absorbed in upper layers. So it cannot reach, means it reaches to the lower layers, but the amount of ionization is less in the lower layers. Fine. So this is the concept which we have seen for all the layers. Okay. Now this is the diurnal variation, although the curve looks very fade, but it is understandable. So this is the diurnal variation. Now what is this word diurnal means? Diurnal means the day and night variation. Day and night variation, or variation whose time period is about 24 hours. Okay, so this is the cycle where the time period is 24 hours. Somewhere it is 12 hours. The half time period is this. Okay, this is the diurnal cycle. Diurnal cycle of the ionospheric layers. So what is happening? What we can see that there are two curves which are there, although shown in blue, but they have written here that this is the daytime curve, this is the nighttime curve. And what is this? The relative electron density. Relative electron density is nothing but you calculate the relative percentage of how much electrons are present. Okay, and this is the height, and it has started from say somewhat 60 kilometers or so, and we know that 60 to 100 kilometers is about D region. After that E, then F1 and F2, which we have discussed already. Now what we can see is that at the daytime all the layers have quite higher electron density, and which is expected. Daytime solar radiation is strong. Solar radiation is strong, right? Daytime the solar radiation is strong, as a result of which the electron density is high. But in the night time the solar radiation cuts off, but whatever the energy which is present over there, solar radiation cuts, but energy present over here helps in ionization. Over there helps in ionization. Now of course it will be not very high as compared to the daytime where the solar radiation is there. Therefore there is a rapid shift from day to the night time, you can see. But the disappearance of the D region generally occurs over these two regions, D and this F1. See, this distance is very small in between two. Therefore E also disappears somewhat, but D and F1 generally disappears at night. Fine. So this is the diurnal cycle. So during the daytime, of course, the electrons will be more because the solar radiation is more, but at the night time, the solar radiation cuts off, although some energy may exist there, because of which the ionization may be happening, but will be not as which is happening in the daytime. So I would say that during the daytime it is like this. For a particular layer, if you go, daytime it is this, but at the night time it becomes this. Again at the next day it is this, and night time it is this. So this cycle is about a period of say 24 hours. Okay, that's why it is called the diurnal variation of the ionospheric layers. Fine. Another term which is also related to these ionospheric layers is the solar maxima and solar minima. Okay, So this solar maxima and solar minima, what are those? Solar minima is the beginning of the solar cycle, and this solar cycle is generally the sunspot cycle. So where the sunspots are minimum, when the time when we see the minimum number of sunspots activities, that is the beginning of the solar cycle, and we call it as a solar minima. Then what is solar maxima? See, solar maxima is the middle of the solar cycle where the number of sunspots are maximum. So maximum number of sunspots is solar maxima. So these two terms needs to be known. What is the solar maxima and what is the solar minima? So solar minima is the beginning of the solar cycle, and solar maxima is the mid of the solar cycle where the number of sunspots activities or sunspots are are maximum, and in case of the solar minima it is minimum number of sunspots. Okay, now what role does it is it playing? Now you can see, check these two curves. Just a minute. Yeah, this is the curve at the daytime, but this is the curve for the solar minima. Okay, but this is the daytime curve. So this is the daytime curve of the solar minima, but this is the daytime curve of the solar maxima. I am not talking about the diurnal cycle now. This is the solar minima and solar maxima during the daytime only. This red curve which I am doing shading. So this is the difference. So as we can see, more the sunspot activities, more will be the rapid will be the ionizations, and as we can see from this values which we are or this plot which we are getting, so more will be the electron density over here, less will be the electron density over this region. On the other hand, during the night time, you can see that this is the solar minima again, that is weak. Of course that will be weak, because the sunspot activities is related to the solar or the release of the plasma, and this plasma generally comes into our magnetosphere and forms certain charged particles, comes through that particular solar storm, solar winds, I would say. When this solar winds comes, these are nothing but from the sunspot activities. More the sunspots are present, from there actually this plasma kind of things comes towards our Earth's surface, and there is a magnetosphere which creates a sheath through which a shock wave region takes place, which creates a resistance to these solar winds, but still certain charges comes into the atmosphere. So these charges are nothing but contributing into the ionosphere. So more will be the sunspots, more will be the charges in the ionosphere. Therefore in the night time also, during the during the solar maxima, it is higher as compared to the solar minima. But the thing to be noted here, just a minute, I will change the color. See this region, what you see is that the daytime solar maxima, which I am representing with blue, the daytime solar maxima, solar minima, daytime solar minima is less than the nighttime solar maxima. This is interesting to see, which we can see from this figure quite easily. Fine. So here, from here, we can see that the daytime solar minima, I would write here, daytime solar minima, this is an observed fact, that's all. Daytime solar minima is less than nighttime solar maxima. So you can understand that solar maxima and solar minima, how big a role in the ionosphere it is creating. Change the color again. The next thing is the D layer, E layer and F layer. I will discuss some characteristics, and then a numerical we will solve. Although I have discussed things about the D layers, E layer and F layer, at what height it is present, where is the peak production height of the D layer, E layer and F layers, and how much electron density is present, that we will discuss here only with a small points. So TEF, and then there is a question, some more about ionosphere, different reactions, combination rate, and then Chapman's theory I would, because it's a long theory, it will take time. Okay. Now, this is the D layer or the D region. So we'll just point out whatever I have said, and whatever I have not said, I will also write it down here. Okay, so D layer, it is the lowest region of the ionosphere. It's the lowest region of the ionosphere. Okay, and its height or the depth is about 50 kilometer to 90 kilometer. See, different places different is written. It is sometimes written as 60 to 100 kilometers or 50 to 90 kilometers, but remember the range, it is in between 50 to 100 kilometers, and it is the lowest region of the ionosphere. No question should be asked by confusing that it will be 50 to 90 kilometer and there is an option of 60 to 100 kilometers. That will not happen. Okay, next is this region. Now, as I was talking about how these ions and electrons are created, now this region is actually produced using Lyman series. This we have studied in chemistry also, you people have maybe studied. So Lyman series, alpha radiation we all know. So this alpha radiation with lambda wavelength of 121.6 nanometer. These are written in the NPTEL slides also. So through this radiations, this region D layer is created. Right? Okay. And this is weakly ionized. Why weakly ionized? Because we have discussed weakly ionized, because energy cannot is mostly gets absorbed in the upper layers, but as you go towards the lower layers, the energy is less. So atoms and ions ions creation and electrons creation will be less. So how much is the electron density? So this is the concentration of the electrons, which is about 10 to the power 8 to 10 to the power 10 electrons per meter cube. And this is during the daytime. Typically during the night time it will definitely decrease. During daytime, night time it will definitely increase, or I would say that D layer actually disappears. D layer disappears during night time. This is very important thing. It disappears during the night time. Okay, mostly ionization of NO occurs. This is the compound whose ionization generally takes place, and peak production is production height, I would say, is about 70 to 95 kilometers, where I have shown that it is about in a table that it is about what you call as 90 kilometers. Yes, 90 kilometers. Okay, fine. This is a very short description of the D region, how it is created. Lowest region of the ionosphere, as I have already told and I've shown you. And this is the 50 to 90 kilometers or 60 to 100 kilometers. It is quite similar region. And region is produced by Lyman series. Alpha radiation, lambda is this. This is also a short wave radiation, you can understand. And this is weakly ionized. Why? Because the electron density is low here. Why this is low? Because the energy in the above layers are mostly gets absorbed. Small amount of energy comes, as a result of which ions will be less produced. And during the daytime, this is the concentration of the electrons, but during the night time, the d layer actually disappears, which is very important fact. Okay, peak production height is about 70 to 95 kilometer, but for one particular height, if you have to say, then it should be 90 kilometers. Mostly ionization of nitrogen oxide, NO, takes place in the d layer. Fine. So this is the full-fledged concept of d layer, whatever we have discussed, and also this extra thing which I have shown. Next is E layer or the E region. Okay, let me write. So for E layer, these are generally at a height of 90 to 140 kilometers. See, these heights may vary. You can see, you can check any particular slides also. This is there also, you can see that it may vary. But remember the range properly, that it should be in between 100 to 150 kilometers or 90 to 140 kilometers. That is the thing. And how it is produced, like in case of the D layer, in case of D layer, we have seen that it is produced by the Lyman series alpha radiation with 121.6 nanometer wavelength, but here it is produced by X-rays, which is about 1 to 10 nanometer. You can see that these wavelengths are very short, and the UV radiation, which you call as that extreme UV radiation also, and it is about 100 to 150 nanometers. Fine. These are produced using this, and in case of D layer, we have seen that ionization of nitrogen oxide took place, but here the ionization of molecular oxygen or molecular nitrogen occurs. And we have written there the daytime electron concentration. Here also the daytime electron concentration is about 10 to the power 11 electrons per meter cube, whereas in the previous it was weakly ionizing, it is 10 to the power 8 to 10 to the power 10 per meter cube in the daytime. Nighttime it disappears. But E layer also begins to disappear. It also begins to disappear at night. But not completely. Remember this. It is not completely disappearing. Sorry, completely. Yeah, it is not completely disappearing. Not disappearing completely. But D layer, you can see that it is disappearing completely during the night, and in fact F1 layer is also disappears during the night. Not disappearing completely. Fine. Okay. This is another thing which I have to make, and mostly the reaction is like this: N2 plus oxygen gives O2 plus nitrogen. This kind of reaction generally takes place near the E layer. Okay, now I shortly discuss about the F layers. See, F layers has two things. One is F1, another is F2. Which one is the higher layer? F2 is the higher layer. F1 is the lower F layer, and this F2 is the upper F layer. Let me see whether I am telling it correctly or not. Where is it? Yeah, F2 is greater than 250 kilometers, and this is 150 to 250. Here also you can see. So this is the upper F layer, this is the lower F layer. What is the height of this? Is about 140 to 200 kilometers, which there we have written as 150 to 200 kilometers, and this one is greater than 250 kilometers. Okay, and electron density over here is about, say, 3 into 10 to the power 11 electrons per meter cube. Not much difference between the E layer and F1. This is 10 to the power 11 of the order, and it is slightly higher than this, but of the same order. But here the electron concentration is about 2 into 10 to the power 12. Now it has increased. But these are all the daytime concentration, and this is the highest, of course, because it is the topmost layer. Okay, these things are there, and in both this F layer, ionization occurs. Ionization of nascent oxygen occurs by extreme UV radiation, which is about 10 to 100 nanometer. Okay, which is also known as EUV, extreme UV radiation. Now, another important thing about the ionosphere is that its critical frequency. Let's give a diversion here. Okay, so this is a diversion I am doing. Okay, so this is the concept of critical frequency. As I will show you in the next slide, there is a numerical question. So critical frequency, what is this critical frequency and what is the concept, why we are using this critical frequency term? This is the radio wave propagation. Radio wave propagation. What happens is that this is the ionospheric layer. Okay, let me write ionosphere layer, and at the surface you have an source, you are giving radiation. Okay, now like this also you have given radiation. Now what happens is that if the frequency of the radiation, let this be F1, okay, this is F1, let's say F2, but I am writing it in general. If F, this critical frequency I generate by Fc. Okay, now if F is greater than Fc, if F is greater than Fc, then wave will penetrate the ionosphere. It will penetrate ionosphere. But if F is less than Fc, that is the critical frequency, then wave will reflect back. What we need is this reflect back mechanism, so that we get the signal to some transmitter. So this radio wave communication generally done using through this ionospheric layer, which is helpful, and this generally goes away because this F1 is of this category and F2 is this category where reflection is taking place. Okay, this is the small concept of the critical frequency which I have shown. Just a minute, now I will change the color and again come to this numerical. Okay, and it's almost done. After that I will go to the Chapman's theory. Okay, this critical frequency which I was talking about, actually its formulation is like this. So frequency is root over 81 times the number of maximum electrons in a particular layer. So this N max, maximum electron density in a layer, right? And this is in per meter cube, right? This is also in meter cube only. So if I do it, this n max here is given. Sorry. So n max is given here. So let us write it given. It's a very small numerical based approach. This is 3 into 10 to the power 13 per meter cube. So if you do it, it will be about 81 into the n max, which is 3 into 10 to the power 13 or if it is in centimeter cube, then you have to multiply by 10 to the power minus 6. Why? Because 10 to the power minus 2 meters is equal to 1 10 to the minus centimeter is 1 meter. Therefore 10 to the power minus 2 whole cube will be 1 meter cube. Therefore it will be 10 to the power minus 6 centimeter cube is 1 meter cube. Remember, this is the conversion. And just a minute. Yes. So now this will be about 81 into 3 into 10 to the power 13, and the root answer is about, say, 4.929. So it's about 49 megahertz. I have given it a very large number of electron density, but as you have seen that maximum will be 10 to the power 12. So if you put 10 to the power 12 here, then what will happen, you see. So it will be 10 raised to the power 12 into, I would say, just 10 to the power 12 into 81. The root of answer is about 9 megahertz or 90 megahertz. So it's a large value. Okay. Just a minute. Yeah. Okay. So this is the answer. Now some more about ionosphere. Well, these things are important. Let me just write it down. So I will write it in very short because I have to go for that Chapman's theory also. It is a large theory also. So ionosphere is more of a quasi-neutral. That means it has both ions as well as neutrals. Right. So three main constituents are N2, O2 and oxygen. Primary ionization mechanism is, let me write it, primary. As you have seen how this D layer, E layer and F layers are created. So primary ionization mechanism is photoionization mechanism is actually photoionization by EUV, extreme UV radiation and X-rays. Or of course for the D layer it is that alpha radiation which is also there. And another process which is the recombination. I will talk what is that recombination reaction just after this. This recombination removes free charges and transforms ions to neutral particles. Okay, and there is another thing, that photochemical equilibrium. Just know that what is it. It's not required. Photochemical equilibrium is that the concentration of electrons will be equal to the concentration of ions. That's all. Okay, so these are the some more concept and what we have discussed so far. Actually, these things we have discussed, these things we have discussed. So these are the some extra things which I have to show, and I have shown it. Now different reactions are there. I will list out certain reactions. Of course, in the NPTEL slides also you can see several reactions are there, but I am showing certain reactions. And then I will talk about the time constant also, and there is a numerical, I have put it here, that will help to solve this particular problem. Okay. Now different reactions. So the first reaction is photoionization. What is this reaction? So as you know that some photons, and if you add with oxygen, it will give you O++ electron. Just ionization, simple ionization using the photons. So that is photoionization. Another is conversion. So there are many reactions corresponding to each of them, but I am writing only one. So N2 plus oxygen give NO plus O. This is the conversion reaction. See, N2 plus oxygen, now NO is combined and O. Third is collisional ionization. So it will collide and ionize. So mostly during the night time, this kind of things may occur. So this is electron plus oxygen gives O plus 2 electrons. Because O2 minus actually. Fourth is recombination, which we are talking about. Recombination. So this is the recombination reaction. So it's oxygen plus N2 gives O2. This combines, and this is N2. So that's why it is called the recombination. Fifth is dissociative recombination. Dissociative recombination, where O2 plus electron gives O plus O. This is another kind of recombination. Sixth is charge exchange. So one's charge will be exchanged to another. This is the charge exchange reaction, which is H plus O plus will give H plus O. Very simple to remember. Seventh is radiative recombination. Radiative recombination, and it is given by O plus electron gives H nu plus O. So these are a set of reactions which I have written here, which you will find in the slides also. Just understand this, what is actually happening, what are the terms which is there, and there is another concept of time constant. So this time constant, tau I would say, is actually alpha into electron concentration whole inverse. Okay, so alpha into electron concentration to the power -1. See, this alpha is actually the recombination rate, and electron, this you know, there is the electron concentration. So this is the recombination rate. So I would show that how it is written, generally in meter cube per second, and this will be in what? Per meter cube. So this will be per meter cube, and therefore this meter cube will cancel, and there will be 1 by second, and to the power minus 1 is actually second. Fine. Okay. So this will be actually second, which is the time. Therefore, it is time constant. Now, based on this time constant or recombination rate, so it is 10 to the power minus 13. If this is the recombination rate, then we call it as dissociative. Whereas, if 10 to the power minus 18 per meter cube per second is the actual recombination. Okay, so this is the categorization of the reactions. Now there is a question. Okay, so there is a question, if the recombination rate, so given the recombination rate alpha is actually 10 to the power minus 9 centimeter cube per second. Now see, this is the same unit which we were discussing in the last, this one, recombination, meter cube per second, centimeter cube per second. Now centimeter cube to meter cube, how to go? It's just 10 to the power minus 6. So 10 to the power minus 6 centimeter cube is actually 1 meter cube. Yeah. Now, so therefore alpha will be actually 10 to the power minus 3 meter cube per second. Okay, and the electron concentration is given to be 10 to the power 12 per meter cube. Therefore, if we combine this alpha into the electron concentration, this becomes 10 to the power minus 3 meter cube per second into 10 to the power 12 per meter cube. Now meter cube cancels out, 10 to the power 9 per second. This is alpha. Sorry, this is the 1 by tau. Therefore, tau will be 10 to the power minus 9 second. Okay. Yes. But something, yes, just a minute. See, 1 centimeter is 10 to the power minus 2 meter. 1 centimeter cube is 10 to the power minus 6 meter cube. Therefore, okay, now this will be, I have written something wrong here. This should be actually 10 to the power 6 or 10 to the power minus 6 meter cube. 1 centimeter cube is 10 to the power minus 6 meter cube. Therefore, this will not be this, but it will be minus 15. I'm sorry. Yeah. So this will be actually 1 centimeter cube is 10 to the power minus 6 meter cube, right? Because this is the small. So 10 to the power minus 15. This is 10 to the power 12. Let it be 10 to the power minus 15. So 10 to the power 3 or minus 3. Sorry, 10 to the power minus 3. Now this will be, therefore, let me write it properly. This will be 10 to the power minus 3, and this 10 to the power minus 3, its inverse. Why? Because tau is alpha electron density whole inverse. Therefore, tau will be equal to 10 cube, that is 1000 seconds. This kind of numerical may be present in the assignment. You can easily solve it. So this is the simple problem which I have said. But remember this particular thing. I have done some mistake over this region. So now I have changed it. Okay. Now comes the Chapman's theory. It will take some time, say about 30 minutes. Half an hour will be enough. Now this Chapman's theory will tell us that where will be the region of the peak production is present, what is the rate of production, how to find out the rate of production, or the peak production we can find out using that, and based on the zenith angles and all these things. And particularly, as I have already earlier mentioned, that this electron density is here and this is your height. So this electron density is high over this region, right? This is what we have seen. So about 250 kilometers, we call this as the region of peak production. Peak production. So why this? Now if you see conceptually, what is happening is that, see, any density, electron density or number density, this is nothing but the number density, right? This is per meter cube. So number density as follows the same curve like the pressure, like the density. So like P is equal to P naught e to the power minus h by h, where h is some variable height and this capital H is kT by mg, or what we write as rdt by g, called the scale height. Okay, this kT by mg is written in terms of the k, which is the Boltzmann constant. In kinetic theory of gases it is used, Boltzmann constant, whose unit whose thing is 1.38 into 10 to the power 23 joules per Kelvin, right? So this is the unit. Okay, so now this rho is also rho naught e to the power minus h by h. Similarly, this number density of electrons n will be equal to n naught e to the power minus h by h, right? Now if this is the thing, then what is happening? So this is the number density, this is the height, then what is happening? As h tending to 0, this becomes n naught somewhere here, and it will reach somewhere at infinity, it will go to the 0. This is the thing, but it is coming out like this. Why like that? Now another thing which we have to consider, this is the number density. Another thing is the intensity of the photons, because that is also resulting into the ions creation. So intensity of the solar radiation. Now as you know, solar radiation is highest at the top and after that it decreases, isn't it? So this is the highest at the top and after that it slowly decreases like this. Now if you combine these two things, what you get is like that curve. Okay, decrease in the upward region, decrease in the downward region, and there is a peak in the middle. So these two combines to form this kind of peak production peak. Remember these two things. Therefore intensity as well as the number density is responsible for the peak production rate. So this is the concept of the Chapman's theory, which I will discuss also in details and derive what is the peak production, although it is also there. Now I quickly write down the assumptions of the Chapman's theory, four assumptions. that I will write and then start the derivation, because that will be a good thing to do, but it will not come. These long derivations may not come in the assignments also. But we can do it quickly for our understanding. Okay. So the Chapman's theory assumptions, first of all, is that the basic concept of Chapman's theory is that ionization, which happens, which is resulting into this production rate, is actually proportional to, or it depends on, the eta, the number density of electrons, the lambda, wavelength, and the intensity. This wavelength and intensity are quite related, but these three things on which the ionization will depend, and some thing like Q is the rate of production, okay, and Qm is the peak production rate, and third is the Hm, the height of the peak production. Okay, so these three things are important. Now I will write the assumptions fast, just a minute. Yeah, so the first assumption is only one type of gas is present in the atmosphere. This is for simplification, only these assumptions are taken. So only one type of gas is present in the atmosphere. Only one type of gas is present in the atmosphere. This is the first assumption. Second assumption is what? Atmosphere is horizontally stratified. Right? Atmosphere is horizontally stratified. Third assumption is incident radiation, whatever is coming from the sun, incident radiation must be monochromatic. Now see, monochromatic means what? One color wavelength means one wavelength. That is not possible. So one wavelength. Okay, this is wavelength. So one wavelength from the sun, it's not possible, but it is simplification of this particular problem. Okay, this is just the simplification to which it is coming. Now the fourth is atmosphere is isothermal. Why I am taking this assumption? Because H is equal to kT by mg is same, fixed. Okay, that's why these four assumptions are taken. Only for simplification, these monochromatic assumptions, stratification, and these things are taken. And atmosphere is isothermal. That means I don't need to vary the capital H or the scale height. Fine. Now I will start the derivation. Will not take much time, I guess. Okay. So now this is the normal. Okay. This is the normal, and this is the incident radiation, and this is the solar zenith angle chi. And let us consider some height, say dH, is height from the surface, and this is the dx, the direction or the path the radiation is traveling. So let me write dx is path the radiation is traveling, dh normal direction height. Okay, therefore the relation between this will be dh will be equal to dx cos chi. Okay, dx cos chi, and then dx will be what? dh sec phi, sorry, chi, right? This chi is the, okay, I have not written. Chi is solar zenith angle. What is that? See, we say that at the noon time, during noon time, sun is overhead, so it is over here, but at some other times it may be here, it may be here. Now we are considering a situation where sun is not overhead. So overhead sun, noon time overhead, represents that the sky solar zenith angle is 0, and as we go in the opposite directions, in different direction, it will be plus and minus, and cos of plus chi and cos of minus chi does not matter much, and it varies from minus 90 to 90 is chi. Okay. So this is an equation which we are getting. Now the intensity change while the radiation is coming in this particular atmosphere through the ionospheric region is A dx rho into I. Okay, the change in the intensity, we will not write the negative sign because it will automatically come in di based on these values. Fine. Therefore di by I can be written as A rho dx, which can be written as A rho sec chi into dh, right, based on this particular thing. Also we know that rho is equal to rho naught e to the power minus h by h. See, this is the number density variation which we are taking, and this is the intensity which we are taking. So all the things are included, and you can see that the formulation which we get will give us that particular graph. If you can plot in different software, or you can plot mathematically, analytically. So I will start here. It is started from I infinity, that's from infinity to some height h where intensity is I. That is di by I will be equal to A rho naught e to the power minus h by capital H sec of chi into dh, and this will go from infinity to h, right? Therefore it will be log of I by I infinity, simple, and this will be, if you write it properly, just a minute. Yeah, if you write it, it will be A rho naught, okay, secant of chi, which is not varying here, e to the power minus h by h. So it will be, you are integrating, so e to the power minus h by capital H will remain, and divided by minus 1 by h. So it will be there, and I will get, sorry, this will be minus a h rho naught sec chi, and e to the power minus h by h infinity to h, so it will be e to the power minus h by h. The second limit will be 0. Therefore this will be the final result will be, therefore I will be equal to I infinity, that is at the top, will be exponential of minus a rho naught h sec chi e to the power minus h by capital H. where capital H we all know which is the scale height. Okay, this we have got. Now this production rate depends on chi, the solar zenith angle, and so of course you can see from here, from here, as the solar radiation is falling at a particular zenith angle, then it is traveling much more of the layers. But if it is in the overhead, it is following smaller region. Therefore, it depends on the solar zenith angle as well. Okay, chi I have already shown, that is the number of electrons or ions, which we have already taken it using the rho is equal to rho naught e to the power minus z by h, right? Or z by h or h by h, whatever. And this is nothing but eta per unit volume. So these two are the particular things based on which it is written. So generally they have got that q, which is a function of chi and height, will be equal to eta di by dx cos chi. Fine. This is the expression which they have got. Okay. Now this is the peak production or the production rate expression. Now we will use this expression to understand everything. Now di by dx, sorry, dh, I'm sorry, I have written wrong, di by dh. What is this? From the upper expression we can, so let me write it properly. This will be say 2, this will be say 1. Okay. So from 2 we can write I infinity, the exponential, minus e rho naught h secant chi e to the power minus h by h times minus a rho naught h secant chi divided by minus 1 by h minus 1 by h and e to the power minus h by capital H. Right? I am sorry, this will be h. So h will be cancelled out, minus will be cancelled out. Therefore, what is the expression which we are getting? So di by dh will be I infinity a rho naught secant of chi, because this is the differentiation, so h will not be 1 by h. Okay, so yes, exponential or whatever the things which are there inside h secant chi e to the power minus h by capital H. Fine. And okay, this is the thing. Now okay, there will be another thing which is the e to the power minus h by h, which is there, that also we need to take. So that will be plus, or not plus, it will be just exponential of minus h by capital H. Therefore it will be I infinity a rho naught secant chi exponential of minus h by capital H minus a rho naught h sec chi e to the power minus h by capital H. Fine. Okay. Now Yes. Then now q, which is a function of chi and h, will be equal to eta I infinity a rho naught secant chi. Now there will be a cos chi term, because which is present here, so cos of chi, and you write the same exponential equation, h by capital H minus a rho naught h secant chi e to the power minus h by capital H. Right? This is fine. See, again I am starting from 2. Let me be very clear. So di dh will be like this expression. So we are getting this h will be cancelled, negative negative cancels in this bracket. So I infinity is there. Now from here I am writing here a rho naught sec chi exponential of this term I am writing here, and this exponential is also there, so that is here. Okay, now I am writing these things, and then q, as per the definition, I am just putting the thing. That's all. Fine. Now what I will do is that I will write it properly. So q chi h finally will be eta I infinity a rho naught sec chi, and cos chi will be cancels out. So I have exponential of minus h by capital H minus a rho naught h secant chi e to the power minus h by capital H, and this is the third equation. Okay. Okay. After this, for peak production, what you need to do? The dq by dh should be equal to 0. For what? Q is equal to qm, h is equal to hm. That's all. So I write, just a minute. Yes. So I write it, the differentiation directly I am writing. So it is eta I infinity a rho naught exponential of minus h, I am replacing with hm by h, minus a rho naught h secant chi e to the power minus hm by h, all I am replacing with that, and the differentiation term minus 1 by h, because there is minus h by h, so that is the minus 1 by h, plus a rho naught h secant chi by h e to the power minus hm by h. That will be equal to 0. So from here, actually from this, we are getting that 1 by h will be equal to a rho naught secant chi e to the power minus hm by h. Right? Therefore, e to the power minus hm by h will be equal to 1 upon a rho naught secant chi h. Right? This is an important expression, or hm by h will be equal to logarithm of a rho naught h sec chi. Fine. Okay. Now okay. So this is the expression number 4. Now when we have got this, then qm will be what? Then qm will be eta I infinity a rho naught exponential of, just h is replaced with hm, and minus a rho naught h secant chi e to the power minus hm by h. That's all. Therefore qm will be eta I infinity a rho naught. I am taking minus hm by h to be common, and e to the power minus a rho naught h sec chi e to the power minus hm by h. Sorry, this is not required. Fine. Now what I will do is that I will put this. So Qm will be equal to eta I infinity a rho naught divided by a rho naught h sec chi from 4, right? This times exponential of the second term, this one. So minus a rho naught h secant chi e to the power minus hm by h. This I am not right now replacing, but I will replace. A rho naught can be cancelled out. Qm will be equal to eta I infinity divided by h sec chi, okay, will be equal to exponential of what it is, minus a rho naught h sec chi divided by a rho naught h sec chi. So it's all 1. Therefore Qm with eta I infinity cos of chi divided by h, and this is exponential of 1. This is the peak production rate, right? And it depends on chi, very important. But we will say that for for noon time, you have chi is equal 0, so cos chi will be equal 1. Therefore Qm of 0 will be equal to eta I infinity divided by h into e. This is an important expression as well, but this is also an important expression. This is 6. Okay, this is the simple expression which we are getting. Therefore this eta into I infinity can be written as Qm of 0 into h into exponential of 1. This is what it is written. Okay, now we can therefore write, this slide is over, I will take one more slide, just a minute. I will take one more slide, yes, and end the last part of the derivation. Okay, so now I will write Q is which is a function of chi and h, is actually what? Therefore, because Q we have written already, just a minute, where I have written Q, this one, from equation 3. So this equation 3 I will put from equation 3, let's see. I will put the eta infinity I infinity as Qm of 0 into h into exponential, right? And a rho naught is also there, so a rho naught I have to write exponential of minus h by h minus a rho naught h secant chi e to the power minus h by h, right? This is what we are having. Now Q of chi h therefore can be written as Q m of 0, right? Now I will take these things. Now how will I take it? Using that the expression here, see, exponential of 1, see this e to the power 1 is exponential of 1 minus h by h, which is already there. What I will write next is exponential of hm by capital H. Now what I am doing by hm by capital H? See, hm by capital H and its exponential is nothing but, see, hm by capital H and its exponential will give me a rho naught h second chi, right? A rho naught h second chi, and that is what we have, a rho naught and h, but chi is 0, right? Therefore it will be a rho naught h, and this a rho naught and h is actually taken care by this hm by h, that is exponential hm by h. Fine, this is clear. Now minus secant chi, which is already there. Here we cannot put chi is equal to 0. We have put here qm is equal to 0, so that's why we have put it. So sec chi, again this a rho naught h we can replace it with e to the power hm by h. Remember, this is not minus, and e to the power minus h by capital H. That's all. Now we can finally write it as qm of 0 exponential of 1 minus h minus hm by h minus sec chi e to the power minus h minus hm by h, and that's all. So q of chi h will be equal to qm of 0 exponential of 1 minus zeta minus secant chi of e to the power minus zeta. That is the final expression. This is the peak production rate, and you can see this particular function, that is exponential of exponential, some c minus e to the power minus zeta. So this kind of function gives this kind of peak production. So that's why in the near the F1 F2 transition at 250 kilometers you can find out there is a peak in the production rate. Okay, so that is where I will end today, and so this all about the ionosphere. Let me just keep the annotations, and yeah, so all things are saved. So we have discussed all the assignment questions of the week 8, and then discussed thoroughly everything about the ionosphere, and so I will stop here. Just a minute, let me stop sharing.